Right now, as you watch this, air conditioning units across the planet are drawing enough electricity to power entire nations. According to the International Energy Agency, cooling accounts for more than 10% of all global electricity consumption, and that number is climbing every single year. The refrigerants inside those units leak greenhouse gases into the atmosphere, gases that trap heat, which raises temperatures, which makes us run more air conditioning, which leaks more refrigerants. It is a feedback loop with no off switch, a machine that feeds itself while the world gets warmer. We treat this as an unsolvable problem, a cost of modern life, something we simply have to accept. But 2,500 years ago, in one of the hottest places on Earth, Persian engineers solved cooling with zero electricity, zero refrigerants, and zero emissions. Their technology worked so well that buildings cooled by it still stand today, still functioning, still outperforming the mechanical systems we replaced them with. And then, in the span of a single generation, almost everything they knew about how to build it was erased. The technology is called a badgir. In English, we call it a windcatcher. But that translation strips away the engineering precision behind the name. A badgir is a tower, typically built above a rooftop, that rises into the prevailing wind currents above a city. Its opening faces the dominant wind direction, and as air enters the tower, it is funneled downward through a narrow shaft into the building below. The physics are straightforward. As the air descends through the constricting channel, basic thermodynamics take over. The air cools. It enters the living space below at a lower temperature than the outside environment, and convection does the rest. Cool air sinks and spreads through the rooms, displacing warm air, which rises and exits through secondary vents on the opposite side of the structure. No compressor, no fan, no electricity, just architecture shaped around the behavior of moving air. These towers are found across Iran, concentrated in desert cities like Yazd, Kashan, Kerman, and Bam, places where summer temperatures routinely exceed 45 degrees Celsius. Some windcatchers are unidirectional, designed for regions with a single dominant wind. Others are multi-directional, built with 4, 6, or even 8 sides, each face capable of capturing wind from a different angle. Walk through the old quarters of Yazd today, and you will see them rising above the roof lines like sentinels. Dozens of them, still intact after centuries, still doing exactly what they were built to do. But the badgir was never a standalone device. This is the part that most people miss, and it is the part that transforms this from an interesting architectural footnote into genuine engineering brilliance. The windcatcher was one component of an integrated cooling system that combined 3 distinct ancient technologies into a single interconnected network. The badgir captured and channeled air downward. Beneath the building ran the qanat, an underground aqueduct that carried cool groundwater through tunnels, sometimes for kilometers, from mountain aquifers to the city. Air from the windcatcher passed over this subterranean water, and through evaporative cooling, its temperature dropped dramatically, far below what the windcatcher alone could achieve. Then there was the yakhchal, a massive domed structure made of thick mud brick walls and a conical roof, designed to make and store ice in the middle of a desert. Using nothing but air, earth, and water, Persian engineers could produce ice overnight during winter and preserve it through the brutal summer months. Water reservoirs called anbars were paired with windcatchers to keep drinking water at near-freezing temperatures for months during the hottest season. The evaporative cooling effect is strongest in dry, arid climates, which is precisely where these systems were deployed. This was not a primitive invention. This was precision engineering distributed across multiple connected structures, each one amplifying the performance of the others. And we do not have to take anyone's word for how well it worked. Scientific studies, peer-reviewed and instrumented, have measured the performance of windcatchers under controlled conditions. Indoor temperatures drop by 8 to 10 degrees Celsius compared to the outside air. Maximum cooling power has been recorded at 9.6 kilowatts at wind speeds of just 4 meters per second, a gentle breeze. Fresh air flow rates exceed 122 liters per second, which surpasses modern ASHRAE ventilation standards, the benchmark used to design air handling systems in commercial buildings across the developed world. When paired with evaporative cooling channels, windcatchers reduce a building's total cooling load by 73%. Optimization of just the head design, the shape and angle of the tower opening, can increase performance by 70%. And the environmental numbers are equally stark. Modern carbon reduction calculations show that a single windcatcher installation saves between 74 and 111 kilograms of carbon dioxide per month compared to conventional air conditioning. These are not estimates drawn from computer models alone. They come from instrumented field measurements taken in real buildings in real desert conditions. The technology works, and we can prove it works. And the proof has been sitting in the desert in plain sight for 2.5 millennia. So the question becomes unavoidable. If it works this well, why did it disappear? The answer is not a conspiracy. It is something more mundane and, in many ways, more damaging. The shift happened during the 20th century, as Iran and much of the Middle East modernized rapidly. Western-style architecture became a symbol of progress. Glass towers, concrete blocks, mechanical systems, these were the markers of a nation moving forward. Traditional building knowledge, the kind that produced windcatchers, was dismissed as backward, as something belonging to the old world, something to be discarded along with donkey carts and oil lamps. And for a while, the economics supported that decision. Cheap oil made electricity nearly free. Air conditioning units could be bought and installed in a single afternoon. Why spend months building a complex tower aligned to prevailing winds when you could plug a box into a wall socket? Urban planning shifted accordingly. New neighborhoods were built with concrete block buildings that had no integration for passive cooling, no orientation to wind patterns, no connection to underground water systems. The old knowledge was not just ignored, it was actively abandoned. And here is where the loss becomes irreversible. The craft knowledge of badgir construction was oral tradition. It was passed from master to apprentice across generations, the precise angles of the wind-catching faces, the proportions of the shaft relative to the building volume, the orientation to local prevailing winds that shifted by season, the integration points with underground water channels. None of this was written in engineering textbooks. It lived in the hands and minds of builders who learned by doing, who absorbed decades of accumulated refinement through practice. When demand for windcatchers stopped, the apprentices found other work. The masters aged, and within a single generation, the knowledge chain broke. Elders in Yaz describe the loss with a clarity that cuts through any abstraction. One woman, interviewed by researchers documenting traditional cooling systems, noted that her daughter's modern air-conditioned apartment is actually hotter in the evenings than the old badgir-cooled home her family once lived in. The air conditioner cycles off when temperatures drop outside, but the thermal mass of the old walls and the continuous airflow of the windcatcher kept the interior cool well into the night. An entire field of proven engineering, validated across 25 centuries of continuous use, vanished not because it failed, but because it was culturally replaced by something louder, more expensive, and measurably worse. But the story does not end in loss. In Abu Dhabi, Masdar City was built as a proving ground for sustainable urban design, and at its center stand modern wind towers. These are not replicas. They are evolved versions of the ancient concept, combining downdraft cooling with solar-powered fans and mist systems that spray fine water droplets into the descending air column. The result is a 5 to 7 degrees Celsius reduction in ambient street-level temperature, achieved with a fraction of the energy that conventional cooling would require. In the United Kingdom, companies now manufacture commercial windcatcher systems for schools and hospitals, providing natural ventilation that meets modern building codes while cutting energy consumption. Computational fluid dynamics modeling, the same software used to design aircraft wings, now lets engineers optimize ancient windcatcher geometries for specific modern buildings, specific climates, specific wind patterns. Hybrid systems that combine windcatchers with solar chimneys or low-energy heat pumps function even in low wind conditions where traditional designs would underperform. Optimized rooftop windcatcher installations have improved ventilation performance by up to 27% in test buildings, reducing overall cooling demand by 6 to 19%. Researchers across the UAE and Europe now frame windcatcher technology not as a historical curiosity, but as a viable pathway to zero-energy cooling, a phrase that would have seemed absurd a decade ago, but now represents a genuine engineering frontier. And this is where the investigation arrives at its real conclusion, the one that extends far beyond any single building or any single technology. We replaced a 2,500-year-old zero-energy cooling system with one that consumes 10% of the world's electricity. We did not do this because the old system stopped working. We did it because we assumed that newer means better, that industrial means superior, that a machine must outperform a building. This is modernization bias, and it is not unique to cooling. Every civilization that mastered hot climates discovered passive cooling independently. The Persians built windcatchers. The Romans channeled air through underground passages. Koreans developed ondol systems that managed heat flow through floor channels. Indigenous peoples across the Americas built structures oriented to capture cross-ventilation and thermal mass effects. These were not primitive guesses. They were engineering solutions refined over centuries of trial, failure, and iteration, developed for specific climates by people who had no option but to get it right because their survival depended on it. The possibility that indigenous engineering knowledge, developed over millennia for specific environmental conditions, might outperform universal industrial solutions is not romantic nostalgia. It is a hypothesis supported by measured data. The physics never changed. The wind still blows across the deserts of Iran exactly as it did when the first badgir was raised above the rooftops of Yazd. The earth still cools the water in underground channels. The thermodynamics of evaporative cooling obey the same laws they always have. The principles that cooled Persian emperors are, right now, cooling buildings in Abu Dhabi and ventilating classrooms in London. The technology was never disproven. It was never surpassed by something demonstrably better. It was forgotten, abandoned in the rush toward a modernity that defined progress as the replacement of everything old with everything new, regardless of whether the new thing actually worked as well. Forgetting, in the end, is not something that just happens to a civilization. It is a choice, made through 1,000 small decisions to stop teaching, stop building, stop valuing what came before. And a choice, by definition, is something that can be reversed. The windcatchers are still standing. The wind is still blowing. The only question is whether we are willing to look up.